All right, we're going to go ahead and start, guys. Welcome back to another lecture. Hopefully, you got a chance to look at the previous lecture. If you did not attend the live stream, you want to make sure that you look at that. We're going to today pick up where we left off. A lot of that stuff, it's a lot of theory, just to kind of show you what this AC stuff is based on, but I'm not going to say that you have to be able to understand every detail of what we went over in the last two videos to get a grasp on what we're going to talk about for the rest of the semester. But what I'm going to do today is definitely important. So you want to make sure you follow along with what I'm going to do today. And please, if you have questions, make sure you interrupt me. Before we start, I think there was one or two announcements. One announcement was homework one. If you look, it's posted. It's going to cover stuff we talked about already, but definitely what we'll talk about today will be useful for homework one. And then what else was there? There was a lab packet. I think I put that out. I don't know when that's due. I can't remember. And then we've been meeting at the school. We met, when did we meet? Saturday, for people to pick up their AC packet with the components in it. If you haven't done that, we'll be there. Well, there should be someone there today at 3, from 3 till 6. Whenever we finish this session, I plan to head over to the school, and I'll be there for whatever remainder time is until 6. And then the last day you can pick the stuff up and I'm aware of will be tomorrow, Tuesday. I think the hours are 3 to 6, but that should be sent to you as an announcement. If you check your announcements, you should find the times there. If anybody has any issue or trouble getting the parts, if you won't be able to do it by tomorrow, let me know. And I don't know if they'll let me take one extras or not. Maybe I can bring some here. But you definitely need to pick those parts up either today or tomorrow, so you have them. For the first lab, obviously you don't need anything. If you saw that packet, that's just calculations that you'll do. Turns out to be pretty important. Lab 2 is the same kind of thing. There's not an actual hands-on lab. You'll look at a video and you'll write some stuff for me. And so we'll get into lab 3 or lab 4 is when you actually start taking equipment. Also, I sent out a link for the meter. You need a digital multimeter. You do not have to use the one I sent you the link for. That was the one recommended by Dr. Whaley. I'll go ahead and probably get that one. I actually have one that I bought from Lowe's for, I don't think I spent 20 bucks on it. So the one that I sent you the link for, Dr. Whaley said he received it in 2 days. I think he got it, I don't know if it's Amazon or you'll see the link. He got it pretty quickly. If you don't want to wait to receive it through to be delivered, then you can, like I said, you can go to Lowe's or Home Depot. They'll sell a multimeter there, and I wouldn't spend you spend 20 bucks for it, you should get a pretty good meter. And then hopefully by maybe the 3rd week or the 4th week, we're ready to go with some hands-on labs. You have all the parts and materials. I am thinking about, I don't know how this will look, but I am thinking about having a few days that we go up to the campus and we actually meet face-to-face. The reason is the equipment that you have, the trainer and the digital multimeter, is useful, but there's a device, as you'll see when you do the next lab 2, called an oscilloscope that we heavily rely on that when we're doing face-to-face labs. And there's no way we can have you purchase one of those, because even an inexpensive oscilloscope will be several $100s, and they can easily run into the thousands. So I want to think about what that'll look like and see if I can look into the details of how, so that we can have at least some of these labs face-to-face, so you can go in and put your hands on the, we have an analog oscilloscope, which are the old ones, and then the new digital oscilloscopes or oscilloscopes. You need to just kind of work with that a little bit. You can do some oscilloscope measurements in multisim, so we'll probably practice doing that a little bit. But at some point, I'm going to try to do at least a few labs face-to-face, but I got to see if I can get, I guess, like security clearance to do that. I do know that there are holding some labs on campus, like for nursing students. Obviously, you can't do those kind of labs through the web. I know the welding students are doing hands-on labs. Auto mechanics, they're doing. So there are students meeting at the school. I just don't know how they're doing it, and the channels to go through. But we'll look and see if we can make that happen. And I will keep you informed on if that happens, how it's going to look. Before we get started, does anyone have any questions for me over anything we talked about regarding the material so far or anything in the class? Any questions at all? Anything I need to review? Anything you're wondering about? Well, I'll tell you what, let's go ahead and dive in. Again, the last two lectures is a lot of theory. Sometimes people who teach this course, I probably will say most of the people who teach this course, they skip over all the stuff we did for the last two lectures and then just jump right into what we're going to do today. I think that if you can understand the background material, it makes the rest of the course, it'll make a lot more sense to you. And then I can reference things that will help you and later on when we talk about some of the other concepts in the course. So again, if you didn't have a chance, I know most everybody was here for the first session. That last session, I didn't get a whole lot of participation. So if you didn't get a chance to see it, make sure you go back and look at it and try to help you understand what we're going to do today. But the end result of that very last lecture, without going into too much of the details of what we talked about, was that we figured out that we can represent an AC waveform like this. So we came up with that relationship, and we also came up with the fact that omega equals 2 pi f. So I want to start with that. The first thing I want to do is name each part of this equation. This is an equation, or we say mathematical model, for an AC waveform. And what we have over here on the left is called the instantaneous voltage. Instantaneous voltage. This one here is the peak voltage. So we'll say peak voltage. It's also called the amplitude. So you want to make sure you know these names. This omega, that's the angular velocity. And then T, that's just our independent variable, kind of like an X in an equation. This is a constant. Omega is usually a constant for a particular generator, and VP, the amplitude, is a constant for a particular generator. The independent variable is the T. That's like the X in a regular equation, and the dependent variable would be V. So I might have something like V equals 100 sine 377t. So you would know the peak value, and you would know the angular velocity. Now, a couple things I want to say about this equation. Number one, notice that I'm using this capital V here for the amplitude, and I'm using a lowercase script v for what we call the instantaneous voltage. That's kind of normal in the AC courses when they teach this. If we're talking about a value that's instantaneous, and what I mean by that is a value whose magnitude varies with time, then you use a lowercase script v. A lowercase script v. For peak values and other values that I'll mention today, we use uppercase letters. So anytime you see a lowercase letter, that means it's an instantaneous value. The value of that particular quantity depends on what time you look at it. And so this instantaneous value is written as a script v. I can do the same thing with voltage, or not voltage, but current. I can have an instantaneous current. And you'll see some other quantities where I'll remind you that that's an instantaneous value. So just kind of put that away somewhere, that anytime you see a lowercase letter, it's an instantaneous value. The other thing is this omega. mentioned the fact, if I go back just to review a little bit of the math, that's called the angular velocity. We know a regular velocity, the regular velocity, let's say, of your car. What you do is you take the distance and you divide it by time. And so this might be in meters, and this might be in seconds, so your speed will be meters per second. Or the distance might be in miles, and this might be in hours, so your speed might be recorded in miles per hour. Well, that's called the linear velocity. I can do the same thing with an angle. The angular velocity, if I take the angular distance divided by time, then we talked about this in the previous lecture, so you can review the video and go into the details. But then this angular distance could be in degrees or radians, and normally it's in radians. So this would be in radians, and this would be in seconds. So angular velocity has the units of radians per second. Now that's a speed. Radians per second is the speed. If you wanted to, you can go through the math. You can turn radians per second into revolutions per minute, or RPMs, and that probably will make more sense to you. You can easily do that with the calculation. So this is what we mean by the angular velocity omega, radians per second. And so what we did here, if you think about it, for that omega, well, a couple things I want to show you here. The argument of the sign, about the sign of something. The thing that you put in there is called the argument. In math, it's called the argument. So the argument here is right here. Omega t is the argument. Omega might be, like I said in the previous problem, it might be 300 or 377. You tell me what to put in there for t, and I can tell you the instantaneous voltage at that time t. Well, so what I'm doing is I'm taking omega. Now look at what omega is equal to. Omega is equal to theta over t. So theta is in radians. This is in radians, and time is in seconds. So I'm taking this, which is radians per second, and I'm multiplying it by t, which is in seconds. And if you look at that, seconds are going to cancel out. So the thing in the argument in here is radians. That's important because when you're doing this calculation on your calculator, you have a choice. You can enter in information. You can take the sine of an angle in radians. You can take a sine of an angle in degrees. You don't want to use degrees there. You want to make sure when you do this calculation, you have to change your calculation, your calculator to radian volts. I'm making a point of that because, like my calculator that I use, comes up by default in degrees, because most of the time we use degrees. But here, I will need to physically go in and change it to radians. If I don't do that, I'll get the wrong answer. Typically, in electrical engineering, what we do, we measure in degrees, but we do calculations with radians. So I might have a protractor where I actually can measure the degrees of something. I can measure the degrees. When I want to do actual calculation with that number, I do it with radians, because degree is an actual unit, but a radian is just a number, like the number 1 or 3. It's just a number, so this is a unitless number. And I don't want to go into the details of that and get sidetracked, but if you want to know more about that, you can ask me, and I'll be happy to share that to you after the video is over. So you want to make sure that anytime you use this equation, your calculator is in radians. If not, you'll get the wrong answer. The other thing that we talked about is the fact that we said, all right, well, since I know that omega equals the angular distance divided by the time, what if I put in here, instead of any old time t, that lowercase t means any old time t. You pick a t, I put it in there, I'll tell you what the instantaneous voltage is. But this t right here, do you remember what this one means? This capital T. The capital T, well, we said that was the period. It's the period of the AC waveform. That's how long it takes for one complete cycle. Or, I'm talking about the generator, every time the generator goes around one time, it makes one cycle of AC current or AC voltage. One time around the circle makes one of these. So the period is how long does it take for that? What's the time for one cycle? And if I look at how many of those cycles go by in a second, then we call that the frequency. So we talked about the frequency. And we figured out that the period is the inverse of the frequency, and the frequency is the inverse of the period. So I gave you those two equations to write down on your equation sheet if you're making one. So if I look at this, the question I'm asking is, all right, I know that omega, angular velocity, is the angular distance over time, radius per second. But instead of putting in any old time, what if I put in a specific time? What if I put in the period? If I put in the period, do I know that theta? The answer is, well, yeah, I just told you. The period is the time for one cycle. And one cycle is 360 degrees or 2 pi radians. So if I say that this is the period, then this right here has to be 360 degrees, because by definition, the period is the time for one complete cycle, and one complete cycle happens when the generator goes around 360 degrees. But remember what I said, we don't ever calculate with degrees. We measure with degrees and we calculate with radians. So 360 degrees is equal to 2 pi radians. 2 pi radians. And so then I said, all right, well, that's interesting. So I got 2 pi radians over the period. That's also equal to omega. But if you wanted to, I can pull that t out and I can write it like this. I can say that's 2 pi times 1 over the period. Now, it's really the same thing. If I multiply 2 pi times 1, I get what I had before. But writing it this way, you can compare it to this and say, hey, I can see that 1 over t is f, and so 2 pi f is another way to write omega. 2 pi times the frequency. So usually what I do, I think I showed you in the last class, I actually put in omega as 2 pi f. But what I usually do is remember the equation this way, but you want to remember that omega is equal to 2 pi f. And if you do that, we can get a lot of information out of the equation. So, having said that, what I want to do is I want to work an example problem that'll help you out with homework 1. I want to work an example problem using this, and I do have that on the topic sheet. If you have that topic sheet out, you want to go ahead and take it out. But there is one more thing I want to do before we get to that point, before we do the example problem. I want to talk about all the different ways you can measure or you can calculate values of AC current or AC voltage. In DC, there's just one voltage, there's one current. But in AC looks like this, but I can report the results different ways. And so we have to be familiar with all the different ways. So I want to spend a little bit of time going over that. And then you make this list, and if you have questions, please ask, because this is pretty important. So we'll do that. I'll list the different ways we can write AC voltages and currents. And then we'll do an example with this. And then I have to talk about one of the values that I'm going to show you. Oh, before we get into that, let me show you one more thing. I forgot about it. You guys know from algebra, you probably know that, let's say I have the equation for a line. I use the point slope equation for a line. So I have y equals mx plus b. That's the general form of the point slope equation for a line. So if I give you a specific equation, I might say y equals 2x plus 1. And you can see that the y-intercept is 1, the slope is 2, but this right here, this x, what is x? Well, x is my independent variable, but the values that I'm allowed to put in for x is called the domain. I don't know if you remember that from your math class. X is called the independent variable, but the allowed values for x is called the domain. And over here, this is my dependent variable. The value of y depends on x, but the values I get are called the range. So this term range and domain are important. So the domain here is X. Well, if I go back to my voltage equation, the script V is equal to VP sine omega t. Normally, as I said before, VP, we know that that's a constant. My amplitude is a constant, and omega is a constant. We usually know those two numbers. So like before, I might write this like V script equals 100 sine 377t. So notice I wrote this as a constant, and I wrote omega as a constant. Typically, that's the way you'll see it, like this. Well, my domain here is X. Here my domain is T. That's the domain. And over here is my range. This is the independent variable. That's the dependent variable. The value I get for V, script V, depends on the value I put in there for T. The reason I'm going through this is because the name of this, when I report an AC voltage or current using a sine or cosine, it's called time domain. So you'll hear me mention that time domain. That means that I'm showing V, the instantaneous voltage, and whatever I'm saying for voltage is also true for current. I mean, there's no reason why I couldn't write the current like a script current equals I P sine omega t. Here, that would be the amplitude of my current. That would be the instantaneous value of my current. And again, I got omega t here. So whatever I'm saying for voltage is also true for current. I'm just going to show it in terms of voltage. So we always know, or we pretty much, just realize this is a constant and this is a constant. So the independent variable there is t, and that is the domain. Like X is the domain here, t is the domain here. So the name of this expression, when you show AC this way, and the current or voltage is time domain. So now we're working in time domain. And hopefully later today, I'll show you a different way to write it. And we'll see how our time goes. All right, so let me show you. Let's make a list. Now, if you read the book or if you look online, they'll probably have some different values. It's the same as what I'm going to show you. But I do every one of these in terms of the peak voltage. And the reason I do that is I think it's easier to remember. I'm going to give you a list of voltages, ways that you can show the AC voltage. And everything's going to be in terms of the peak voltage. But if you look online or in your book, they might use multiply by 1.41 or the square root or something. They might have a root 2 or a 1.41 constant that they multiply by. Well, it's all the same thing if you work it out. But I'm just saying I use V peak in everything because it's easy to remember. So I don't care how you do it, as long as you know the equation, I'm good. So let me show you what I'm talking about. It's easier to show you than it is to say. So I can have this. Peak voltage or amplitude. That's one way. I can also have the VPP, and that's called the peak to peak voltage. So I can give you a graph like this. Suppose I gave you this graph. And I told you that's 50 volts. And so down here would be minus 50 volts. And I show you the AC waveform. I say the AC waveform looks like this. So there's your waveform and it keeps going. Well, one cycle of this waveform starts right here and it ends right there. That's one cycle. And the peak voltage, V peak, the peak voltage or the amplitude is right there. So I would say my peak voltage here is 50 volts. Now I have to have a VP here, or if I just show this as V equals 50 volts, then you want to put a PK over here so that we know it's a peak measurement. If not, I don't know which one of these it is. So either you'll say VP is 50 volts, or if we don't have the P there, you can say V is 50 and put a PK here, or a P there. Probably a PK for P, because it makes a little bit more sense. But I can also get the peak-to-peak voltage, which is just I measure from here to there, and from there to there, and I add those together. I don't take into account that that's negative, because I know a negative 50 is a 0. When I'm saying the absolute distance from here to here, the absolute distance is 100. So the peak-to-peak voltage is just twice the peak voltage. So if I want to calculate this, VPP is just 2VP. And the reason for this right here, having the peak voltage and peak-to-peak voltage, is when you actually measure AC, you use a device called an oscilloscope. And it's not so much true today, because the digital scopes do everything for you. I mean, you can have the IQ of a donut hole. As long as you know where things are, it does everything for you. The old ones that I was brought up on, you actually had to know what you were doing. So what I'm going to have you guys is use the old one, get some experience with that, and then you'll go to the digital one. And it's all menu driven, and as long as you figure out where things are, it does all the thinking for you, which I think is a double-edged sword. It's both good and bad. You know how to use it, but you don't really know what it's doing. It's like magic. So I have you use the analog first, so you know what you're doing, and then you move over to the digital one. Okay, so you got the peak voltage or the amplitude, the peak-to-peak voltage, and then there's this one. Sometimes we'll show it like this. And that stands for the average voltage. That's the average voltage. So let's talk about that a little bit. Well, right off top, if you're thinking about this, we got a problem. Let me show you what the problem is. Let's just take one cycle of a sine wave. Let's take one cycle of a sine wave. The new one looks like this. And I want to find the average value for that sine wave. Well, how do you find the average of anything? So you find the average. If I wanted to find the average score on the test in the class, what I would do is add up all the scores and divide by the number of students that I have. Well, that's exactly what you would do here. If I want to find an average, what I would do is I add up all these values. So let's say I take a value here, I take a value here, I take all these values all the way across, and now I add all those up. And then I would divide by the number of values I have. The problem is, if I do that for the whole sine wave, for every positive value I have here, there's an exact value over here that's the same, but it's negative. So the average here, if I take all these positive values and add to all these negative values, I'm going to get the 0. The average of a sine wave is 0. I'm adding positive values to the same negative values, it cancels out. So this average is, when you see that, I want you to be aware, because I don't know if it points this out in the book or not. When you take the average of the sine wave, they're not taking the full cycle average. They're only taking the half cycle average. They start here and then go here. Then they did the whole thing, the average would be 0. And you might think to yourself, well, okay, well, is that any good? What is the half cycle average? Well, and what we're going to do in this class is not really important. I don't want you to know how to do with the average value, is how to get it. But it does have application, and I'll just briefly tell you what the application is. And we mentioned the first day of class that the reason we use AC voltages and current is because it's much more efficient to transmit energy in the form of AC compared to DC. with DC, there's a lot of losses. With the AC, I can use a device called the transformer, step the voltage up, which drops the current. If I send the energy out, high voltage, low current, it's much more efficient that way. And we kind of went through the details of that, so I won't bore you with that right now. But once you get the AC power, or once you get the energy in the form of AC where you want it, you step it back down to a low voltage, high current, and then you can use that to run your vacuum cleaner, your whatever. We also mentioned that most devices that you would actually use, like your computer or cell, most devices, not all, but most devices are DC devices. The reason for that is it's easier to, for the most part, it's easier to design a device for DC than it is AC. Everything, all other factors being equal, if I was going to design your cell phone, I can do one that's strictly AC, one that's strictly DC. The DC design will always be simpler. So usually what we do is this: move power around in the form of AC because it's more efficient to do that. Once we get the power where we need it, we change it from AC to DC. So even though you think you're plugging your cell phone in the wall and it's taking in AC, what it's really doing is it's taking in AC, then there's circuitry inside of it that converts the AC to DC. And so to do that, what they do is this. I'm just going to show you a little bit of this because I don't want to go into the details. If you want to go into the details of this, you need to take an electronics course because this is kind of the stuff they talk about in electronics. But what they can do is, using devices, we can actually take this part of the cycle and flip it up so that it looks like this. So we have circuitry, it's called rectification circuitry, that actually takes this and flips it up and makes it positive. And so now I still got remember here's my peak value, that's my peak value. Well, I still have that down here. I still got my peak value. But this half of the sine wave never swings negative. So this actually is, if you think about it, this right here is DC. That's not the kind of DC you're used to seeing. You're used to seeing DC like this. Over time, you're used to seeing the voltage or current stay constant. But this is DC called pulsating DC. This is the kind of DC that you get anytime you take AC and convert it over to DC. And so if you were to use this DC, you should be able to take your digital multimeter, put it on DC, and you should be able to measure a voltage here. Now, you can take your digital multimeter and put it on DC and measure AC with it, but what you're going to read is 0 because the average value of AC is 0. But if you do the same thing to this is the rectified waveform. When they flip this up, you will actually measure, the value you will measure would be an average value of all of this, be average, and then value can be calculated using the value over here that I'm going to show you. So that turns out to be important. And if you really want to know what happens in the rectifier circuit takes your AC, it takes this part of the sine wave and flips it up, makes it positive. So now I have, this is AC, and down here I have pulsating DC. And then what they'll do is they use circuitry called filters to, what the filters will do is it'll kind of take out, you see I got these humps, it'll fill that in. And so what I get is something more closer to regular DC with a little bit of variation there. So any kind of device that you plug into a wall that takes in AC but really has a battery and uses DC, it has this circuitry in it called a rectifier. And again, if you want to know more about that, you can ask me about it when we're not recording, and I'll be happy to go into the details of it. But this value right here, the average value, this is the value that a DC voltmeter would read. If you feed it pulsating DC, you would get that by this. V average is equal to 0.637 times VP. So if you multiply, so in other words, let's say my peak voltage So that peak voltage right there was 10 volts. Then my average voltage would be 10 volts times 0.637, which will give me 6.37 volts. So if I'm given this waveform, if my peak voltage here was 10 volts and I ran it through a rectifier circuit, the circuit would flip that negative half cycle up, make it look like this. If I take my DC voltmeter and hook it up to this waveform, it's going to read about 6.4 volts. You can actually run DC stuff off of this. It wouldn't work. I mean, it could cause some issues if you have something that, not that you'll mess anything up, but it can be a little noise. Really, you want to filter this to make it look like this. But technically, you got 6.37 volts of DC. You can actually use that to power something if you wanted to. Like a motor wouldn't care. If you had a 6-volt motor, it wouldn't care if it had this 6 volts or this. But where you might have a problem is if you have something like that plays music, like your cell phone or something like that, and feeding it pulsating DC directly might introduce noise into it or cause some other issues. So it just depends on what you're doing. So we'll never really use this directly, but know how to get the average value, know that it's the half cycle average, and know that it has applications. If you take more of the electrical courses, you'll see this again if you take electronics. I know I mentioned that some of you are electromechanical, or you might have a major to where you take AC and you take DC and AC, and you don't take electronics, you don't take digital, or you take digital 1 but not digital 2. And that's why I kind of push you guys to take a double major, because it's kind of bad that you go into AC, DC and AC. AC kind of puts everything together, but then you really never see what you do with it, because courses like electronic device, you never take it. You don't take it if you're electromechanical. And so if you're electromechanical, what I recommend is go ahead and go through your electromechanical degree, but with the addition of 2, maybe probably more like 3 or 4 other courses. And if you play the game right, you can actually take all these courses and get two degrees. And you know these courses that kind of feed off DC or feed off digital, you'll take all of that. You get the full picture. So I'm a big fan of that. I know some of you are paying for this, and you might want to hurry up and go get a job and all of that. And I understand that if that's the situation you're in. But if you have time or money, I highly recommend it. I highly recommend taking. Once you take AC, you can take anything that comes after. The prereq would be DC and AC. I would highly recommend taking an electronics course, and I would highly recommend taking digital, at least digital 1, but hopefully digital 1 and 2. Anyway, we'll save that for another talk. So we got the peak voltage or amplitude. We got the peak-to-peak voltage. Again, we just use that when we measure off the oscilloscope. Sometimes it's easy to measure here. The oscilloscope has a grid on it. It's like it looks like an Excel spreadsheet where each square is 1 centimeter by 1 centimeter. And so you can actually read vertically or horizontally. If you read from top to bottom, you read in one quantity. If you read horizontally, you read another quantity. So you got to measure like you're using a meter stick or a ruler, using a metric ruler. And sometimes it's easier to make the measurement. If I have a big waveform, I can measure from here to here, just the peak value. But sometimes the waveform might be really small like this, and it's easier to measure from that peak to that peak, the peak to peak. So these are just for measuring purposes. The average, I told you, anytime you rectify AC, you change it from this to that, then the average value is going to be important. And if you're wondering, where the heck did that 0.637 come from? Well, if you take, I don't know how many you've taken, I know you had algebra trig, but down the road, if you take a calculus class, one of the things that you can do in calculus is you can integrate. I'm not going to go into what it is, but if you had calculus before, you know about integration. If you integrate the area of this curve, you'll end up with this 0.637. So this number, this constant came from calculus. We'll just suffice it to say that. So we got the peak value, peak to peak, the average. Let me give you the other one. Now this next one is actually the most important. Let me give this to you. Very, very important. So this next one called VRMS. So VRMS, that stands for root, that stands for mean, and that stands for squared. RMS, root, mean, squared. The root here, what I mean by that is there's a square root. The mean, I don't know, that's a kind of an average. If you had statistics, you know there's different ways to take an average with the mean, the mode, and the medium. I think this was the mean, the mode, and the medium. I think that's, I said it correctly. But this is a special kind of an average, the mean. And then squared is just what you think when you take something and you square it. So this has something to do with the way this number is calculated. There's a root, there's an average, a mean that might have some integration or some calculus in there. I don't really remember the details of it. But these letters come about from the way it's derived mathematically. So this actually is pretty important. The RMS value is very, very important, critically important. Now it actually has another name that I like better. So I'm going to show you both names. The other name for RMS is the VEFF. That stands for the effective value. The effective value. So RMS and effective are the same. Okay, so write this in your notes, they're the same. Usually I'll talk about the RMS value, even though I like the effective value name better. Most books will call it RMS. But I'll tell you, when I explain what this is, and I'll explain why I like this better, I think it'll be self-evident why I like the effective value. I like for things to say what they are. So, you know, I like for you know, like if you're writing a program and you have a variable in the program, you can call it X, or you can call it tax rate. You know, it's better. I like when things reflect what they really are. And so this kind of says what this really is. So we'll go into the details of that, and you'll see what I'm saying. But all you need to know now is how do you calculate it? Well, the way you calculate it is you take 0.707 times the peak value. And again, that number right there, if you're wondering where that 0.707 came from the same place that this came from. So do some math, they do some math magic, and you get that constant 0.707. So write yourself a note that this is also called the effective value. So of everything that we're going to talk about, this is really, really important for the class. I mean, all the values are important, but for this class, understanding what this is important. And the fact that we have this is going to allow us to do some calculations where if we didn't have it, this class is a lot harder. So there it is. And now you can see what I'm saying, that I write everything in terms of the peak value. So if you know the peak value, you can get all these other values. Okay, so now if you have the topic sheet, I have a printer here at my house that I bought because, you know, this class, and I don't know what's wrong with it. Sometimes it prints, sometimes, most of the time, probably like, I'll say 8 times out of 10, I hit the print button, it says printer offline. I don't know what the heck is wrong with it. Then I'll be sitting there a day or two later, and it'll print automatically. It may even print something I never even asked it to print. Well, today when I turned it on, it just started printing. Well, the computer stays on, but I think I started working on it online, and it just started printing something that I had asked it to print like 3 days ago. And so I said, well, hell, since it's printing, I printed out every document I need for your class for the next couple of lectures. So I got all this printed out, and I don't have to go up to the school to do it. It scans perfectly, but the printer works when it wants to. So I don't know what that's about. But if you do have that topic sheet, go ahead and take it out. The topic sheet from Module 1. And the very first thing there is the electric generator, Faraday's law, sideways force on a moving charge, the right hand rule, and basic generator construction. We spent 2 days talking about that. The last 2 videos, that's what that's about. This next part, though, AC terminology, is where you see the list of all of these. I have here the peak value, the peak-to-peak value, the average value. I got the RMS value. It has a star by it, like I put a star. That's showing you what's important. And then they got frequency and period, and a couple other things like wavelength, angular velocity, phase. We've talked about most of that. So I actually want to go in and do a calculation with this. So what you got, I don't have a calculator, so what I need you guys to do, go ahead, I'm going to pause for a minute, get your calculator out, and I need you to help me calculate. And what you can do is, if you want to say something, is open your mic, give me the answer, and then mute your mic back, and then that's how we'll do it. Okay, so get the topic sheet. And at the bottom of the topic sheet are 10 practice problems. And I'm going to make some room. I'm going to erase this. And I'm going to put up the problem. And actually, you guys take it out. If you have it, you can go ahead and work the problem. I'll be quiet for a minute, give you a chance to work it. If you don't have it, I'll put it on the board. It says given, and they give you this waveform that V equals 167.5 sine 455t. So this right here, that's my argument. And what they want you to calculate is everything we just got through talking about. They want you to find the peak value. They want you to find the peak-to-peak value. They want you to find the RMS value. They want you to find the average value. They want you to find the instantaneous voltage at 3 milliseconds. So when I have an equation like y equals mx plus b, I can write that in function notation. Remember functions? I can call this f of x instead of y equals mx plus b. This says that y is a function of x. I can write it this way. So this is a regular old way. This is function notation. And the reason this is good is because I can say f of 3. And what that means is to take 3 and put it in for x. So I can do the same thing here. I can say v of t equals sine omega t. And this said whatever goes here is what you put in for there. So I'm showing that right here. The way I'm doing that is v, I'm putting in 3 milliseconds. I'm using what you call a function notation that you learned about in your algebra class. So I'm just using that here. And just for the purposes of space, I got that. I got number 6 is the frequency, and number 7 is the period. So I'll stop there. We still got 3 more, but I'm out of space now. So I'm going to be quiet. You guys take out your calculator, the peak value, the peak-to-peak, RMS, average, the V at 3, the instantaneous voltage at 3 milliseconds, give me the frequency, and give me the period. Be quiet for a few minutes to let you calculate, and then we'll do it together. And then we'll finish up the other 3. So go ahead and do it. While you're doing that, I'm gonna go get I have a cookie in the car that's probably hot as hell right now. I'm gonna get my cookie while you guys calculate. I'll be back. Okay, so the way you do this, to think about it, is I always write the general form, which is, let me erase this. So the general form is this: V equals VP sine omega t. And what we had was V equals 167.5 sine 455t. Now, it's probably better, just so you know, to put this in parentheses like that. So you know that this whole thing, the argument is not just the 455. It's actually 455t. So I have a bad habit of leaving that out because I think it should to be there, but not every student understands that it's there. But if you write it this way, then you can kind of relate these variables to each other, and then the rest just kind of fall out. So right here, the peak value, well, that's this. The peak value is that. So for my peak value, I got 167.5 volts. And so write it like V peak equals 167.5 volts. I can write it that way. I can say V equals 167.5 volts. If I don't show the P here, I want to put a little PK over there so I know which one of these the voltage is in. So you want to get used to the notation. And no, that's a capital V, not a lowercase. A lowercase v means an instantaneous value. So we're showing caps here. It's not instantaneous. Now, once you get that by inspection. So you just look at the equation, you got it. But now I need your help with this. How do I calculate the peak-to-peak value? Tell me how to calculate it and give me your answer. So just what you can do is unmute your mic, tell me how you got it, your answer, and mute it back so we don't bog the system down. Anybody get a value for this?
Just double the peak.
Yeah, double the peak.
Okay, so I'm going to go 2 times this. And that's 300 and something. What is it?
355.
I put it over there. Okay, so double the peak value. And then this one, I'm going to take 0.707 times the peak value. What do you get when you do that?
118.42.
118. Now, so this 118.42 actually has a very important meaning that I need to go into the school today. I want to try to get there a little after 4, so I don't want to rush on this. I want to make sure that you understand exactly what this number means. That's very important. So it's giving you information that we may get to it today. We'll have to see. It's like 255 now, so I don't know. We'll see. But anyway, let's get the average value. This is 0.637 times the peak value. What do you get when you do that?
$106.69.
6.69 or 6.5?
69.
Okay. So what does that mean? What does it mean? Well, here's what it means. It means that if you took the AC waveform with the peak voltage of 100, let's just say 168. So that peak voltage from there to there is about 168 volts. About 168. If you rectified that, to rectify means through special circuitry, you take this part of the waveform and the circuitry in this part. Anything that's negative, it'll flip it up and make it look like this. So I got this, which is this one, but now that is flipped up. So that one is there. This is already positive, but then the rectifier will flip that up. So now I've changed that AC to pulsating DC. If you take your digital voltmeter and put it on DC, not AC, this isn't AC, you put it on DC and measure it, what you would measure is about 107 volts. So it's equivalent to a 107 volt battery. You can think of it like that. It's really not, but it kind of is. I know that kind of sounds crazy, but that gives you that equivalency. Okay. And again, please, if you can take I don't teach electronics. I think they let me teach it one time. But the guy that teaches it, he's been teaching it for like 20 years. He don't want to give it up. But if you can take the class, there's some really good stuff in that class. You'll talk about rectification circuits, 3 or 4 kinds of circuits. We'll talk about transformers in this class, but you actually use them in the electronics class. And you'll talk about amplifiers. So it's a good class. If you can take that, I highly recommend it. All right, so let's keep going here.
Can I ask you a quick question?
Sure.
This is Brady, by the way.
Yeah.
Would you put, like, if we had something like that on the test, would you put DC instead of or AC? I just put 0 because I thought you were talking about AC. I didn't know you were putting DC. For the average for the sine wave would be a 0 if it was in AC, but in DC it's what you have there.
Right. So in AC, if I took the average, you're right. If I took the average of the whole sine wave, I took that average, it would be 0. But this right here, this average refers to not the full sine wave, it refers to half the sine wave. So you might want to write a note. That's the half cycle average. We never take the average of a full sine wave. We always take the average of a half sine wave because of the very problem you're pointing out. I'll take the average of the whole thing is 0. So in AC, anytime I talk about the DC average, anytime I talk about the average value, I mean the half cycle average. So you're going to use this calculation right here. So on the quiz, if I say, all right, give me the average value of this sine wave, it's going to be this one. And that's the half cycle average. Okay? Anybody else? Yeah, if you take electronics, this is going to make a lot more sense to you. Right now, it's just a number with not a lot of meaning. But if you take electronics, you'll say, oh, okay, I see how we use that. And it's kind of cool the way it's done. So I think you guys would like that class if you took it. But again, I know time and money are constraints, so not everybody can take a double major and do all that stuff. I stayed in school forever. I think I was in college, got like 3 degrees. I stayed in, so I just loved one. If I could be a professional student and get paid for it, I would have done that forever. So, but when I got to graduate school is when I just said, I'm a graduate school dropout. So I'm the lower guy on the totem pole. Okay, anyway, for this one, I got that written in function notation. So if I actually write it out, V of 3 milliseconds is 3 times 10 to the minus 3 seconds. I'll leave the units off. Equals VP was 167.5 sine of, and then you got to put the numbers in here. So let me get rid of this. Sine of 455 times t. Well, t is this number. 3 times 10 to the minus 3. And that's what you want to put in your calculator. Remember, though, the argument here, all of that is in radians. If you put it in, you should, what I would do if I were you, do it the wrong way. Put it in there in degrees. And then do it the right way. Put it in there in radians. You'll see you get 2 different numbers. And you don't want to make that mistake on the quiz or exam. I have students make that mistake and they lose points, and I don't want you to do it. What I'll do on the quiz, if I give you anything in time domain on the quiz, just write it, go to that problem, put your calculator in radians, do the problem, get your answer, and then take it out of radians because everything else will be in degrees. This is the only time you put your calculator in radians. So do that first so you don't forget, get your answer, and convert it back to degrees. But if you put your calculator in radians and you do this math, tell me what you get for V of 3 milliseconds. What do you get?
163.9.
Right. I think that's the correct number. And I'll tell you why I think that in just a second. But anybody else get that number?
Yes.
Okay. So we're gonna go about 164 volts. All right. Now, the frequency. We want the frequency. Well, let me go back. Let me get rid of this and go back to what I had before. So we know the expression V script is 167.5 sine 455t. And in general form, it's V equals V peak sine omega t. So let's jump down to, well, I guess I don't have it here. But you can see here for frequency, you can see that the angular velocity is this, just by looking at the equation. So the angular velocity, omega, equals 455 radians per second. That's how fast the generator coil is turning that's creating a sine wave. So to get the frequency, remember the equation I asked you to remember that omega equals 2 pi times the frequency. I know this side, I know omega, I can solve for frequency pretty easy. So frequency is going to equal, now watch how the units work out. It's going to equal omega over 2 pi. So omega is 455 radians per second divided by 2 pi radians. The radian is really a number. It's not a unit. It's kind of interesting the way they do it. It's a number, but you can think about it as a unit when you need to. And that's like right here. You'll see it cancels. So if you divide this, 455 divided by 2 pi, can somebody give me the answer to that? What's the frequency? $455 divide 2 divide pi. What is that? Or do it like this if you want. 455 divided by paren 2 pi close paren.
$72.41.
All right. So let me go ahead. Look at this here. I got radian per second divided by seconds. Well, if you do the math there, you'll see it actually works out. This means I have radians divided by seconds. I'll put that over 1. Well, to do that, I just change that to multiplication, and I invert. Did I do that right? Yeah. I have seconds over 1. Wait a minute.
It's radian per second time radian.
This right here is invert seconds. That's it. Say it again. I got that wrong, don't I? I wrote it wrong. It's radians per second. Radians per second. That stopped me dead in my track because oh no, the units don't work out, but they gotta work out. So it's radians per second, and what I did, I put a second there. I should have put a radian. So that's actually radians, like that. So what I actually have is radians per second divided by radians over 1. And then if I change this to multiplication and I invert that, I get 1 over radians. And then what will happen is The radians are canceled, and I end up with 1/seconds. Well, if you might remember from in the last video, we said for frequency, the frequency unit is the hertz, but the hertz is equivalent to an m-second, so I can write it like that. So I'm just showing you the unit actually works out. But anyway, you're going to write this as about 72 hertz. So that's your answer. And then when they want the period, well, if you got the frequency, you can get the period and vice versa. The period is 1/the frequency. So when I do it like that, since I want this in seconds, I'm going to show this as 1/seconds. So this is 72.4 1/seconds. So what is 1 divided by 72.4? How much is that?
That's 0.013.
Like that?
Yes.
Okay, seconds. Or 13 milliseconds. That's the period. Okay, so remember I said, I think it was Jacob when I asked about, what was it? I think it was this one, that one. And I said, I think that makes sense. And the reason I said that is, you see what time we looked at it? Around 3 milliseconds. We're saying 3 milliseconds into this waveform, the peak was what? The peak is like 168 if we round it. So 3 milliseconds into this waveform, we're almost like at 164, which is close to that. So if my period is 13 milliseconds, watch how I think about this. If you think about it like this, if my waveform, when I know this is, I know that my peak value right here, my peak value, I know is that. So that's about 100, I'm going to round it to approximately 168 volts. So that's my peak value. Well, I also know from here to here, according to this, it's about 13 milliseconds. Let's just say 14 just to make it easy. So 13 to 14 milliseconds. So this would be close to kind of 7 milliseconds or a little bit less than 7. And then so this right here should be around 3.5 milliseconds. So once you get around 3 milliseconds, I'm getting close to my peak value. So when Jacob said, when he did this calculation right here, he said that's around 164. Well, if 3.5 is there, 3 is probably like right there, and that's probably, yeah, that's about 164 volts. So that's why I said I think that's pretty much the right answer. So all this stuff got to make sense. And I think when you do that homework 1, it forces you to think like this, and it'll make more sense to you. So we got the frequency, 74 hertz. We got the period, 13 milliseconds. I think there's 3 more things we got to talk about here. Number 8, number 9. Look at number 9. Number 9. If anybody misses that, you're gonna get slapped. Well, I better not say that. I got in trouble last time because I forgot one of my sayings, but somebody in the class didn't like it. So you got to know I'm joking when I talk like that. I just look to get the angular velocity. So the angular velocity, number 9, it says, what's the angular velocity? 455 radians per second. Now, what would be neat is to convert that radians per second to a more useful unit, RPMs. Usually in the States, when we talk about something spinning, we talk about revolutions per minute. So you can actually take this from radians per second to revolutions per minute. That would be a good exercise to do. A really good exercise to do. But anyway, so number 9, I'm not going to talk about. You just look at it. That's omega. But number 8 and number 10, let's talk about those two. Number 8 and number 10. And I'm going to clean the board up while we talk about those, number 8 and number 10. All right, so number 8, they want you to find something called the wavelength. The wavelength, what the heck is that? The wavelength. And then they give you a hint. So let me show you what they have in case you don't have the paper. They tell you to find the wavelength. And then they give you this hint that says C equals lambda F. They give you that. And they also tell you that C is equal to 3 times 10 to the 8th meters per second. So what is all this stuff? Well, first of all, let's talk about C. C is the speed of light. It's a constant, fundamental constant, a fundamental constant. C is the speed of light, 3 times 10 to the 8 meters per second, 186,000 miles per second. F is what you think it is. It's the frequency, but this is it looks like an upside down Y. That's a Greek letter lambda. Lambda. That's a Greek, and we use that for wavelength. So the wavelength of a signal. Say this is my waveform. The wavelength is just from one repeating part to the other repeating part. So if I want to, you see this point right here and this point right here repeats. So the wavelength would be that. And the unit for this is meters. So it would be in meters. So you're measuring between these 2 points in meters. Now when I do wavelength, another repeating point is start here and then there. It's like a cycle. So the wavelength would be the distance from there to there. The distance in meters along here, that distance in meters, the linear distance. That's the wavelength. Now, let me tell you a little bit about this. I don't want to go off, but I don't want to go off on too much of a tangent, but it just speaks to the diversity of this course, how this course touches every other course in electronics. It turns out that when you have an AC current flowing through a wire, so right now, I got an extension cord. You guys can't see mine. I'm in the basement, and I got a light here. You probably see the reflection over here. I got 2 lights down there. I got a window over there, and I got a light above my head, but I keep that off because if I turn that on, it puts a reflection in the board, and I think it makes it harder for you to see. But what I want to say is this cord to this light I have over here, there's an AC current in here. Anytime I have AC current, remember what you learned in DC. In DC, you learned that anytime you have a current flow, you have a magnetic field around the conductor the current is flowing through. It's impossible not to have a magnetic field. Anytime you have a current, it's going to be associated magnetic field. Well, in AC, since I have a varying voltage, I have a varying current. It varies like a sine wave. And so what I have is, in AC, I have a magnetic field that's changing, but I also have an electric field that's changing. Anytime you have a current, you have an electric field and you have a magnetic field. But if it's AC, that change actually causes it to radiate into free space. So some of the energy, some of the AC energy in here is actually radiating off as a wave, actually 2 waves. One that looks like this, and one that looks like a sine wave. One sine wave is doing this, and one is like flat, it's doing that. So I got it vibrating this way and this way. That sine wave is actually, one of those is the electric part of the wave, and the other is the magnetic part of the wave. So what I'm saying is, if you run a current through a wire, some of it's going to radiate off into free space. It looks just like the sine wave that's in the cord. The energy that radiates off is called electromagnetic radiation. And that happens anytime you have a varying AC waveform in a conductor. You get a wave that actually travels at the speed of light away from the wire, and it is two sine waves. It has a electric component and the magnetic component, and the two together is called electromagnetic radiation, abbreviated EMR. And this is the basis, EMR is the basis for radio, TV, your cell phone, a wireless cell phone. Anything wireless is using this fact right here. When you use your cell phone, even though you don't see it on the outside, on the inside of your cell phone is a built-in antenna. And that antenna is just a piece of wire. And what they do is they run an AC waveform up and down that piece of wire and actually radiates energy. You call it a radio wave. You're actually talking, when you're talking to your cell phone, we can get this EMR carry information. It can carry voice information. It can carry picture. It can carry video. Whatever you can send through your cell phone, you're doing it through this electromagnetic radiation. And so the point is that we don't really talk about the wavelength of a signal in a wire. You could, but once the signal leaves the wire, once it radiates from the wire, we have a radio wave. We can talk about the wavelength of that radio wave. You might say, well, why would you want to do that? Well, the reason you want to do that is if I want to capture that wave, I want to receive it. I have a transmitter transmitting a radio wave, and somewhere else I got a receiver. Your cell phone is a transceiver. A transceiver is a transmitter and a receiver. Your cell phone can transmit a signal, it can receive a signal. But so it's two things put together, a transmitter and a receiver. So when you're receiving a signal, that signal comes in and it hits that antenna and it induces, we use that word induce in DC, you might not remember it. It induces currents and voltages inside your cell phone, and those currents and voltages are carrying information, whatever was transmitted to you. So the point is this, I know it can get kind of deep, but your antenna needs to be either a wavelength to receive the information properly. It needs to be either full wavelength or some multiple of that wavelength. Okay, so a full wavelength or some multiple of it. So if you're in the communications, wireless stuff, it pays to know that if you're going to design an antenna to pick up the radiation that's leaving the wire, you got to know what size to make the antenna. You have to figure out that wavelength. Okay, so let's do that. The problem here says that what's the wavelength of if I know the frequency, let me go back to here. I know the frequency is, I think we calculated about 72 hertz. We'll just leave it at 72. Or 74, is it 74? I think it was 72 and some change. I think it was 72 hertz. Okay, so let's just say that's our frequency. I want to know the wavelength. So what I can do is I can use this equation and I can calculate that wavelength. So if C was lambda F, lambda equals C divided by F, right? And they're telling us that C is 3 times 10 to the 8 meters per second divided by the frequency, which is 70, was it 70? I can't remember 70 or 74. It's not going to matter. It's going to be really close either way. But let's just say it's 72. Now, even though this is hertz, I want the units to cancel, so I'm going to show this as an inverse second. So what I need for somebody to do is to take your calculator and put in 3 times 10 to the 8, that's 300 million, divide 300 million by 72, and let me know what you get. What do you get? Three times 10 to the 8 divided by 72.
It's 4167 66666.6 repeating.
Dang, that's the devil number right there, isn't it? All right, well, we're going to leave it like that. Let's just leave it like that. So that's 1, 2, 3, comma, 1, 2, 3, comma. Now, this would be, this will cancel. This will cancel with that, and my units will be meters. Now, the problem is I don't know how many, I don't have a feeling for that many meters, but I do know miles. So do me a favor. If you got your phone or your computer in front of you, bring up Google. Just bring up your Google search engine and put this in Google. That's 4,166,666 meters. If you go into Google and say, put in that number and say 2 miles. I want to convert this from meters to miles. I don't know how many miles that is. So go ahead and do that. Let me know how many miles that is.
It's 2,589.
2,589 miles. Okay, so here's what I want to like this wire right here. Now this is actually pretty close because this is plugged into the wall outlet, and in the United States we use 60 hertz, which is not too far from 72 hertz. So what this means is the distance from this point to that point in meters, that distance is this, 2,589 miles from there to there. So if I wanted to, right now, there's a signal being radiated from that wire. If I wanted to pick that signal up properly, my antenna would have to be this big. I need an antenna almost 2,600 miles. Let's see, from here to California is about 5,000 miles. So from right here in Cincinnati, halfway to California, my antenna would have to be that big. And obviously that's not practical. Well, let me show you something. Look at this. Or some multiple of that. But look at this relationship right here. C is a constant. That's the speed of light. We can't change that. But look at this. The higher the frequency, the smaller the wavelength. The smaller the wavelength, the smaller my antenna can be. So in your cell phone, you don't even see the antenna with your cell phone. Most people don't even think there's an antenna there. It's actually built into the phone itself. It's really, really, really tiny. The reason it's really, really tiny is because cell phones use a really high frequency, probably gigahertz. The frequency is so high that way they can make the antenna really, really, really small. That's one reason for that. And there's other benefits to having a high frequency like that, but there's trade-offs. So, typical broadcast frequencies, I don't know if you, AM, there's AM, that stands for amplitude modulation, and there's FM, that stands for frequency modulation. We'll talk a little bit about that later in the course. But typical frequencies here is about 1,400 kilohertz. And typical ones here might be like 103, but this is megahertz. So antennas for AC or for AM were way, way, way bigger. AM came before FM. And so the antennas were huge. It had Voice of America up on, I think it was 75. They had a radio transmitter up there, and you would see these big, huge towers, which were antennas for AM. The Voice of America, I don't think, I mean, it exists. I don't think the one up the road exists anymore. FM, the frequency is on the order of megahertz, so I can make the antennas a lot smaller. So, again, I don't want to go off on too much of a tangent, but this has so many applications and so many fields that this course is a must. And then to help you, if you do take a communication course, you'll think back to this class and go, okay, wow, that was some good information. Anyway, anybody have any questions over this? Well, I'm going to move on and finish out that sheet. It's 3:30 now, and I want to get to school and help pass out some of those parts. So, Yeah, anybody have any questions? I can talk about this stuff for hours, and I don't want to bore you. Anybody have any questions over what we went over? This is not, I'm not going to test you over this. I just put that on there because I thought it was interesting. I want you to see how this ties with communication electronics. It all ties together. So any questions over any of this stuff? Well, there's one more problem on the practice sheet. It says if the waveform is placed across a circuit consisting of a 100 ohm resistor, find the RMS current and the expression for the instantaneous current. So in other words, now I have an actual circuit. So let's draw the circuit. And this is the kind of stuff you'll actually do in this class. So you have a circuit. It's just a simple circuit with a resistor. So I got an AC source, and I don't know if I showed you this, but that's the way you draw an AC source. And I got a resistor. And there's my voltage. There's my resistor. I know that's 100 ohms. And they tell me that this voltage is V equals 167.5 sine 455t. That's the value of this. And so what I want to know is two things. I want to know the RMS current, and I want to write this as a function of time. Like this right here, I can show that as a function of t, since I have a t right there. What expression would I write for I? So I can write it like an instantaneous value. So let's do this first, the RMS value. Anybody get that value already? Well, how would I get that RMS value? What would I do? Anybody? So remember all those values we had over here? Peak value. Ohm's law, it doesn't matter if it's AC or DC, Ohm's law always applies. So if I want current's always going to be voltage divided by resistance. But now I got choices. If I put in the peak voltage, I'm going to get a peak current. If I put in the peak-to-peak voltage, I'll get a peak-to-peak current. If I put in an average voltage, then this value is going to be an average current. We want RMS. So if I put in an RMS voltage, it'll give me an RMS current. So let's do that. I'm going to put in, let's find the RMS value of this. Well, we already did that. VRMS, I forgot what it was. What was it? Was it 118? What was the RMS value we calculated for the voltage?
It was 118.42.
Okay, so I'm just going to say 118.4 volts RMS. I'm dividing that by 100 ohms. If I divide that by 100, I'll get IRMS is going to equal 1.184. This time it's going to be amps RMS. If I show RMS there, I don't have to write it on that. But if I just had it like that, then I got to subscript that RMS. But I like to put it over here. I think it's better if it's over there. But there's the answer. So the point is, whatever voltage you put here, peak to peak, whatever, it's going to dictate. That's 1D. It's going to dictate what you get out for current. So if I use an RMS voltage, I get an RMS current. So that's not too bad. Now, that's this one. That was easy. Now, how do I get the expression for this, for I of t? Given B of t, how do I get I of t? And again, I'm going to use Ohm's law. I go back, I use Ohm's law. Ohm's law says that if I want I of t, I take V of t and divide that by R. Now notice that there's no t on the R because resistance doesn't vary with time. Current varies with time. The voltage varies with time. So I can put a T here and there, but resistance is just resistance. It doesn't care if it's AC or DC. It's going to stay whatever it is. So there's no T there. But if I divide this, then that means I have this whole expression divided by R. So I'm going to erase this V of T. I'm going to put 167.5 sine 455T. I'm going to divide that by R. That's 100 ohms. Now, when you do the math here, all you're doing really, if you think about it, is just dividing this right here. And this right here is going to stay. So this is V over R, right? V over R. And so, and it's a peak value because I want my amplitude to be in the peak value. So if I divide this, this will be 1.675 sine, and this stays the same, 455T. And this will give me the current, instantaneous current, or you can put a T there if you want to show it in function notation. So here's the instantaneous current, there's the instantaneous voltage. Again, this is just Ohm's law. Put it up here for your notes. Is what we did. Okay, so that's actually pretty simple. All right. Anybody have any questions or comments? Okay, so if nobody has any questions, do I have a question? Oh no, that's something else. Okay. All right. I could talk about RMS. I want to talk about RMS, what it is and what it means. I just want to know. That might be a good place. Let me do that. Let me finish up by talking about RMS, what it means, and then we'll finish. That way I'll be closer to 4 o'clock. And then next time we come together, I can use the information that we're going to get from that. So remember, I said one of the ways to express a voltage or current is as RMS. So let's talk about that, and that'll get me close to 4 o'clock, and that's kind of where I want to be. And then I can run over to the school and pass out some of those kids. So what is the meaning? And I'm saying the physical meaning. What's the physical meaning of RMS? It's also called the effective value. To help us to understand that, I'm going to show you a little experiment, a thought experiment. We're just going to think about this, a thought experiment. So I want you to think about it like this. Imagine that I have some water in a pan. Let me put it over here. So I got water in a pan. So I'm just going to show it like that. So I got water. In the pan, I have a resistor. So I got a resistor. And I got it hooked to a switch and a battery like this. So I got a switch, and I'm going to make this 100 volts. It could be, that's not important what it is. So you can see what's going to happen. When I close the switch, current's going to flow, the resistor's going to get warm, it's going to heat the water up. So what I need here is a thermometer. So I'm going to put a thermometer in here. And what I want to do is, I want to figure out what the temperature of the water is. So let's say in the thermometer, it goes up to like right here. That's my starting temperature right there. We'll call it T1. I close the switch for a certain amount of time. So what I'm doing is, over time, I'm going to apply voltage or current for a certain amount of time, and then I'm going to open it. Well, what's going to happen is, when I close this, that resistor is going to heat up because it's dissipating power, and the mercury is going to rise from there up to some other point. Let's say it goes all the way up to right there. I'm going to call that TDC. So I got my starting temperature, and this is TDC. This is the temperature from hooking up a DC source. It went up that high. Then what I do, open this back up, and when I do that, this is going to go back down to the starting point. All right? Now what I do is I take this out, and I'm going to replace it with an AC source. I'm going to replace it with this. But not just that, my AC source really looks like this. You might remember, when I draw an arrow through something, if I have a resistor, that's a fixed resistor. If I show this like that, that means I can change the resistance value. So I can have it with a voltage source. I can have this, or I can have this. This is a fixed voltage source. I can't change it. This is a voltage source I can dial from 0 up to some maximum value. So I'm saying here I have an AC voltage source that's variable. But in AC, whereas over here with this one, all you can change is voltage. Over here, I can change the voltage, or I can change the frequency. This is what I want to change. So what I'm going to do is I'm going to turn this all the way down to 0 volts. So right now, I got 0 volts of AC. And then what I'm going to do is close the switch. I'll close it. And I'm going to start to turn this up just a little bit. I turn it up, and when I turn it up, what's going to happen is that AC is going to do exactly what the DC did. It's going to heat that resistor up a little bit, and the mercury is going to rise up. So I turn it up little by little. I just edge that up. I turn it up a little bit more, and it gets a little higher. What I want to do is turn it up slowly until the temperature is exactly what it was before. TAC. So I slowly keep increasing this until that water is heated up by the AC source exactly to the same temperature that the DC source hooked up to. That was hooked up. Once that happens, once I get TDC, the DC temperature, and the AC temperature exactly equal to each other, then what I know is, I know that both the AC source and the DC source are doing the same amount of electrical work, because the result of work is heat, and if I'm getting the same amount of heat, they're doing the same amount of work. So really what you're doing is you're equating AC to DC. If I started with a 100-volt battery, I think we said the DC, we had a battery, it was 100 volts. If that 100 volts causes the temperature to go up here, then when I put the AC source in there, and the temperature goes up to the same place, then this AC voltage source is doing the same amount of work as that. Effectively, it's doing the same work. So the question is, what value of AC would do that? What value would do that? Well, that's what the RMS tells you. RMS, VRMS, or I'm going to call it effective for now. V effective equals 0.707 times the peak value. So let's say that my DC voltage is 100. I want to figure figure out effectively how much effective work is this thing doing to make it equal 100 volts. My effective value is 100. The question is, how much actual AC peak voltage do I need to get this voltage source to do the same amount of work as a 100 volt DC battery? How much? And all I got to do is solve this for VP. VP equals 100 divided by 0.707. Can somebody do the math for me on your calculator? 100 divided by 0.707 is what?
141.4.
141.4 volts peak. So I need a peak voltage over here of 141.4 volts. I need the peak voltage, 141 volts peak of AC to do the same amount of electrical work as a 100 volt DC battery. So it takes less DC to do the same amount of work as AC, or it takes more AC to do the same amount of work as DC is a better way of saying it. And you shouldn't be surprised at that. I mean, look at this. If, let's say that my DC, let's say my DC is like this. This is my DC. Let's say I have a switch on and I turn it off, but I turn it off right here at T over 2, where T is the period of an AC waveform. So I have this is a DC waveform, right? It's DC, I close the switch, and I turn the switch off at this time right here, T over 2, where T is the period. Well, if it's the period, then what I'm saying is my waveform, here's my waveform. If this right here is T, that's my whole period, T over 2 is right there. So I did this on purpose because that means that half of this fits in that box like this. If this is T over 2. So if I look at the DC is the purple box, the AC is the green. So I'm looking at half the sine wave. If I turn that DC switch off so that it goes to 0, half of the AC sine wave, you can see that the AC is only doing work for this shaded region right here. Whereas the DC is doing work there and here and there. So it takes more AC to do the same amount of work as DC. So what the RMS value gives you is the effective DC value. What size battery would it take to do exactly the same amount of work as this AC waveform? If you say that I have something that's 120 volts RMS, which is what you get in the wall outlet in your house, you got 120 volts. You might not know it's peak to peak, or what it is, but the voltage in your house is 120 volts RMS. That means it does the same amount of electrical work as a 120 volt battery. Effectively, it's the same. That's what the effective value. Effectively, it's the same as a 120 volt battery, DC battery. That's what that means. Now, we're actually going to use that next class, so I'm glad I got that in. I did it in like 15 minutes, so it's pretty cool. Anybody have any questions on what I just talked about? The thing to remember is that RMS deals with heating effects, and it equates, it's a way of equating AC to DC. So, you know, think of DC as dollar bills and AC as pennies. You know, I got 100 pennies, I can have $1 bill. Both of them do the same amount value-wise, but it takes a lot more pennies to make up that thing over here I'm calling a dollar bill. It's kind of the same idea over here. So this is actually going to be very, very important to understanding the next topic. And that next topic is going to allow us to do pretty complicated calculations using AC, only because of this fact right here that I take an AC waveform and equate it to a DC waveform. But I'll have more to say about that later. So if nobody has any questions or comments, I'm going to end the class here. And I'm going to head over to Cincinnati State now. I'll be there probably definitely before 4:30. And I'm going to pass out some more parts. So if you didn't get a chance to come over Saturday and get your parts for the lab, you want to come over there, come up the College Drive off of Center Parkway. and you can only go one way. They got it blocked off. Just go into lot D, and we'll be right over there to the left. You'll see at that wing over there that sticks out. You'll see us over there passing out parts. So if you didn't get a chance to come up Saturday, come by. I'll be there till 6 o'clock. You can pick up your parts. If you don't do it today, you'll have to do it tomorrow, because tomorrow's the last day we'll be passing out parts. All right? Anybody have any questions or comments? I will see you guys later. Have a good one.